In this example problem, we will take a look at two loudspeakers in a plane that are 2 meters apart and in phase with each other. Both emit sound at 700 Hz in a room where the speed of sound happens to be 341 meters per second. The listener stands 5 meters in front of the loudspeakers and 2 meters to one side of the center. And what we're trying to answer is the interference at this point maximum, constructive, perfect, destructive, or in between? How will the situation differ if the loudspeakers are out of phase? So let's take a look at what this looks like. So to start, our listener is 5 meters away from the front of one loudspeaker and 2 meters away to one side of the center. The loudspeakers are 2 meters away from each other. So here we have our two loudspeakers. They're 2 meters away, emitting sound at 700 Hz. The big dot there represents where our listener is. So that listener is 5 meters away from the front of the loudspeakers, but 2 meters away from the center line that goes between our two loudspeakers there. Because they're in phase, we can see that our inherent phase difference is 0. So now let's take a look at the mathematics going on in here, now that we've seen what our picture looks like. So to start, what we need to focus on is the distances R1, so from one speaker to the listener, which again is 5 meters away. And for that closer speaker, it's a distance between the speaker and the listener of only 1 meter. So using our distance formula, we find that that distance is 5.1 meters away. For the second speaker, it is also 5 meters away in the horizontal direction, but this time the listener is going to be 3 meters away from the lower speaker in our diagram. Distance formula again, and we find that our distance to the second speaker, the further speaker away, is 5.83 meters. Our path length difference then is going to be the difference between these two distances, so R2 minus R1. If you plug in those numbers, you'll see that that is 0.73 meters difference. So our path length difference is 0.73 meters. Great. So we've got our path length difference. We still need to know what our wavelength is. So we know what frequency is. So we can use our relationship between velocity of the wave, frequency, and wavelength. We'll move that around to solve for wavelength. So our speed of sound for this problem is 341 meters per second. Our frequency was 700 Hertz. Go ahead and divide that through, and you'll see that the wavelength we're talking about is 0.487 meters. So if we want to take a look at our path length in terms of how many wavelengths it is, we'll divide our path length difference by the wavelength. And find out that this is 1.5. So now notice that our units cancel. So this is basically like saying that our path length difference is 3/2 of the wavelength. So since our sources are identical, meaning our inherent phase constant is 0, this means that we're talking about destructive interference. If our phase constant was pi, then we'd be talking about constructive interference. Now let me go through and show you mathematically how we're able to figure this out, but you could tell just by looking at a half of a wavelength that meant destructive. If you were looking at a whole of the wavelength, then you'd be looking at constructive. So in either case, our sources are in phase, so that goes to 0. So then we plug in our path length difference. Again, plus 0. We can cancel some 2's. So we'll see that our phase difference is then going to be 3 pi. So since this is an odd multiple of pi, again, that means destructive interference. Since we are talking about identical sources, you also could have seen this just from the path length difference as well. So if our inherent phase difference was pi, meaning these sources were out of phase, then our phase difference would be the 3 pi that we got from the path length plus that inherent phase difference of another pi, which would give us 4 pi, which is an even multiple of pi, which means you'd be talking about constructive interference.